Okay, so we will be recording. If anybody has any objections or inconveniences with the recording, please say so now. If not, okay, then we're going to continue. So first learning module is electrostatics, and the first topic we're going to be talking about is electrical charge and Coulomb's law. And so first we need to understand what electrical charge is and how electrical charge is not necessarily created, how electrical charge is transmitted, and how it's generated. It's not necessarily created, but it is generated or transmitted between objects. So electrical charge, one way to define it, and I believe we were talking about this last week, I believe it was Giselle that gave us the definition, which is basically this: the electrical charge is a basic property of matter. Now, this is important in definitions. Basic property of matter. That means that all matter has this property. We have it. This spoon has it. The table has it. The walls have it. The house has it. Everything. The soil has it. The earth has it. Everything. It's a basic property of matter. That has to do with some elementary particles. And what are these elementary particles? Well, having to do with electrons, protons, and everything that composes the atom. That governs how these particles are going to interact or be affected by an electrical or a magnetic field. Okay. Now, electrical charge can be positive or negative. That's something very important from now on, that I think it's a bit different from when we were talking about statics or dynamics. We're not only going to be talking about forces interacting, we're also going to be talking about how those forces are going to be directed or oriented based upon the signs or the sign interactions, okay, of the elements. It occurs in discrete natural units, okay? That means that there are going to be units associated to the electrical charge, and it can neither be created nor destroyed. It's only transmitted. Second concept that's important for you guys to remember: the unit of measurement, or the discrete unit of measurement of an electrical charge, is the coulomb. Okay, it's the coulomb. And this is because there was a gentleman, last name Coulomb, that did work relating to that. And from now on, it's the units that are used. Not the Thor, by the way. The Thors are units for something else. There's actually units that are Thors or something like that. So there are a couple of images of Thor, as I've mentioned before. I don't know why I have this sort of man crush with Thor. I like the movies. I'm not particularly that big of a fan of the comics or anything like that, but I really enjoy the movies. Ragnarok is kind of like a comfort movie. I really enjoy the movies. And so we've got the god of thunder there. How is electrical charge generated? Let's talk a little bit about that. But before we do that, can anybody think about a phenomenon relating to electrical charge that you have experienced in your life?
Thunder?
Excuse me, can you repeat that?
Thunder?
Thunder? Thunder is thunder. The way I would define thunder is an instantaneous discharge of a huge amount of electrical charge between the atmosphere and the earth. I'm going to repeat that. That's a Sosa definition of thunder. I don't even know if it's Britannica accurate or anything like that. Thunder is going to be this instantaneous discharge or transmittal of electrical charge between the atmosphere and the earth. So that's a good example, Lisette. That's a phenomenon. We've seen thunder. I hope none of you have been struck by thunder. Okay. There's this thing about, let's do this. This is a sort of like a mental gum Homework task. No, not homework task. You don't have to turn in anything. But have any of you heard the phrase "lightning never strikes the same place twice"?
Yes.
Yes.
Research why that is. Based on the definition I gave. Research why that is. I'm going to ask. Not now. Next couple of classes, I may ask if anybody found out that. That's a good example. That's a good example, Lisa. Remember to turn on your cameras if you're going to participate so I can see you, because I have the strip.
I forgot. Sorry.
No, but don't worry, Lisa. You popped up, but since I have the strip on this side, I don't see everybody. That's a good example, Lisa. Give me another example of electrical charge you've experienced. Anybody? Don't tell me you've never been to Walmart, particularly in Calexico or El Centro, and you're moving your cart with somebody next to you, and suddenly, what happens?
In the Museum of Sol del Niño.
The slide.
Yeah. I wasn't answering your question, Professor.
I noticed that, but go ahead, please, Lisa. And if you could turn on your camera, that's fine. And I'll go back to my question. What example were you giving, Lisa?
I don't remember what was it, but it was like a ball, and you put your hand, and it gives you this charge.
The good example, Lisa. That thing, it's called a Van de Graaff generator. It's actually something we're going to see here in class, and it's an example of something that can create that generates this electrical charge. That's a good example. It's this ball that suddenly you hear something that's kind of moving in there, and then suddenly you touch it, and your hairs go up, or you get a shock. Thank you, Lisa. That was a good example. I'm going to go back to my question now. Have any of you been walking someplace and suddenly you say hello to someone and something happens that has to do with electricity and electrical charge?
You get, oh,
Go ahead, whoever wants to participate, but turn on your cameras, please.
you get like a shock, like a tick.
Yeah, you get a shock, and depending on
Small
what's
shock.
happening there, it could be even painful or at least very bothersome. Those are examples of electrical charge phenomena. But how are those phenomenons? What's happening with those phenomena? Well, how can we generate this and by the way, just to not be not confused, we said that electrical charge isn't created or destroyed. So we're gonna use the term generated by not being a synonym of created, but generated means transmitting electrical charge, or having something to be electrical charge. So none of you mentioned this phenomenon, and I'm sure you've done it at some point. That you grab a balloon and you start shaking the balloon in your hair, particularly. And what happens with the balloon once you do that? I know you've done this experiment at some point. So you rub it on your hair, and then what happens? What do you do with the balloon, and what happens? Oh, come on, you have not had a childhood. It sticks to you or to any other surface. It might stick to the wall. Okay. But before you rubbed it in your hair or on your clothes, that didn't happen. Well, there's an electrical charge phenomenon happening there. There are many ways in which we can generate electrical charge. And so one of these ways is answering this question. How is electrical charge generated? By friction. We can have two surfaces, and by rubbing those two surfaces, electrical charge is generated. Why is that happening? Because in the end, we're comprised of atoms. Friction generates the atoms to start moving. that movement makes electrons within these atoms start to vibrate, and depending on the movement and the materials, the electrons are going to start jumping someplace. What is that someplace? Again, since energy is neither created nor destroyed, it's going to be jumping to some place where there aren't any electrons. And you guys, if you remember your chemistry classes, in an atom, there's going to be orbits where there are electrons. So there, with certain types of energy, I can make electrons pop out or move, start moving. Once an electron pops out of the orbit, there's a hole there, or there's a space where another electron can go there. And so friction can create these movements of electrons, and electrons are transmitted from one place to the other. That's what's happening with the situation here. So we've got the balloon, which we're going to say it's in equilibrium, meaning the positive and the negative charges are the same. Then we've got somebody here with a lot of hair where it's also balanced. And once there is friction, the movement is going to be generating jumps of the electrons from one place to the other. And there's going to be one surface that's going to be charged with one polarity, and there's going to be another surface that's charged with another polarity. So I don't know if you've done the same exercise, though. You're rubbing the balloon, and the balloon sticks to the wall, but suddenly if somebody touches you, suddenly you discharge something because you've also been unbalanced with regards to your electrical charge. So friction is one way of doing it. There are many ways to generate charge. The other is by induction. So does somebody know, has somebody heard the term induction before?
Yes.
What does induction mean? Yes, or what do you think it means when I do something by induction? Yes, whatever you think.
That you are like, I don't know, that's
It's
The
fine to
part
answer. It's fine to
you are-
answer. I don't know, by the way. But go ahead.
Oh.
I'm sorry. I interrupted. I'm sorry.
that you are drawing that you are like dragging the item to the thing. I don't know how to explain it.
Well, the thing here, Yesel, the rest of the group is in friction. In friction, there is contact. Would you agree with that? So to have friction, I have to have contact with the two surfaces. Well, in induction, there is no contact. When something happens by induction, it means that I'm transferring one type of energy from one place to another without there being contact. So whenever we talk about a phenomenon that has to do with induction, it means that there's no contact. So when electrical charge can be generated by induction as well. There are certain phenomenon where, for example, you notice that everywhere that there are cables, electrical cables, they're shielded, right? I mean, you don't have an electrical cable where there's the copper or the wire or the wires just plain. It's always shielded with some other material. That is not just for the protection of us, that if we touch it, we could get hurt. It's also because the movement of electrons can induce electromagnetic phenomenons in other conductors that are close by. And that's why I'm gonna ask you for another homework task, which is gonna be weird, and that's gonna be for next week, for the long weekend, but I'll let you know now. Have any of you watched the movie The Prestige? It's a movie where it's Hugh Jackman, Christian Bale, Michael Caine. and David Bowie. Has any of you seen that movie, The Prestige? Well, it's too old. It's not that old, the movie, but you're probably still too young. I'm going to ask you to watch that movie because the movie has to do with magic. And there's a reason why what the prestige means. And it has to do with magic. But curiously enough, one of the side characters in the movie is Nikola Tesla. And why am I mentioning this? Electromagnetic phenomenon. I'm gonna go kind of Dungeons and Dragons here, but probably in medieval times when they thought there were people that were sorcerers, right, that did magic. I can say with, I believe, a certain high level of certainty that these people that other people thought were sorcerers were actually very smart people that knew how to manipulate two things: electromagnetic phenomena and materials. That's what alchemy is in the end. It's combining materials to create other materials. Why? Because since electromagnetic phenomena, you can't see it, you can generate certain phenomenon that's invisible. So something interesting that happens, if I have a conductor, a cable that's transmitting electrical energy, and there's current going through it, and I grab another cable where there's no current going through it, and I just put it close to there, the other cable is suddenly going to have an electrical current. Another thing, if you probably did this experiment, but if you grab any sort of core, you can grab a pencil and just grab a cable and wind it around the pencil and connect that cable to a battery. What are you going to generate? What is going to be created? Did you do that experiment maybe in high school or maybe primary school or kindergarten or whatever? There's going to be a magnet that's going to be generated. So there's going to be a lot of electromagnetic phenomenon. So for example, the example that Lisette gave of the Van de Graaff generator, where you touch the generator and suddenly your hair starts to go up, or you get an electrical shock. Imagine that it's not Museo Sol del Niño. Imagine that it's medieval times. And some guy said, you know what? I noticed that if I rub these two materials, there's something that's being generated, some sort of energy. Well, what if I put those two materials on a wheel, on a sort of a conveyor mechanism, and I start turning it, and then I put a metal round thing around it? The metal is going to start to get charged. So I can have a box and have somebody turning it, and then I can tell people, come over, and magically I'm going to give you a shock, and I'm going to make your hair raise with this device. It looks like magic, but it's not magic. It's electromagnetic phenomenon. And so friction can generate electrical charge, or induction. Those are two examples of generating electrical charge. Nuclear phenomenon can also generate electrical charge, as has been seen. Okay, I'm gonna remember, if you guys have any questions, please let me know. Any questions up to this point? Okay. Are you guys still alive at least? Estrella, please go ahead.
Oh, I just wanted to make sure that induction means that they are transferring atoms, but without having contact.
Exactly, and that can be done. So part of the electromagnetic phenomenon is actually, as I mentioned, you can have two objects depending on the materials. Right now in this example, Estrella, it's the balloon and you're rubbing it, but you could actually have two objects that without touching, but being very close to each other,
They're still transferring.
the energy barrier can be brought down, and there's going to be transfer. Actually, in the Van de Graaff generator that Lisette mentioned, this thing where you touch it and you get your hair raised, in some situations, depending on how strong the Van de Graaff generator is, you don't even have to touch it. You could just get close to it with your hands, and suddenly your hair is going to start going up. That's by induction. The energy levels have to be strong enough to break an energy barrier for the electrons to go from one object to another, but it can happen. And so friction is with contact. Induction is where there's a transferal of energy without contact. Oh, by the way, and thank you for this is a good question, Estrella. Induction, these phenomenons that I'm mentioning are not only for electromagnetic phenomenon, they're also for thermal phenomenon. Have any of you heard of induction ovens? So in a normal oven, you turn on a flame and the flame is generating the energy that's heating everything. So there's a flame that's having contact with a surface. There are these ovens, and even I believe grills, where actually, I don't know if you've seen these, there's this oven and there's the grills on top, and you can actually put your hand on the grill and you're not going to get burnt. But if you put a certain, I forgot the name of kitchen.
Depends.
Pan, thank you. If you put a pan of a certain material on top of the stove, it's going to start getting heated. So
You
there's
notice
actually,
like the types of material.
exactly, because of the types of materials, and it's done by induction. So there's no flame. Why doesn't it happen when you touch it? Because the combination of materials aren't going to generate that. So those are some examples. So these electromagnetic phenomena also happen in some cases with thermal phenomena. So that was a good question, Estrella. And I think, Ricardo, you had raised your hand as well.
I was just gonna ask if one way we could think about it is that induction is kind of like wireless connection. It's like
Exactly, a wireless connection is
like a
you are getting transmissions to your cell phone and you're not seeing it, and it's not by contact, right? And that's also actually an electromagnetic phenomenon. Any sort of transmission of waves, that's an electromagnetic phenomenon, because part of what we're going to be seeing is that the weird and interesting thing about electromagnetic phenomenon is that on one side you can analyze them as particles, and on the other side you can analyze them as waves, and there's different variations on that, but it's the same phenomenon. So yeah, the wireless is another example of something that's not done by contact. Good example there, Ricardo. I was on mute. And so there, something that's very important here, and this is important from now on, is that since electrical charge is a property of matter, then electrical charge and electromagnetic phenomenon and other physical phenomenon are going to depend on the materials and interactions with materials. So there are going to be certain materials that lose electrons. These are materials that lose electrons very easily. That only means that in their atoms, in the last orbit, there are so few electrons that the energy to make them pop and jump over to somewhere else, you don't need that much energy. There are going to be other materials that gain electrons. So these are going to be materials that have spaces in them, or it's very easy to be able to make connections between atoms, and so they can gain electrons. And so depending on the combinations of these materials is how you are going to generate this electrical charge. So these are some of the materials. So you've noticed that depending on if you're wearing a sweater, and depending on your shoes, on the type of clothes you're wearing, and you're walking around and suddenly you're generating electrical charge because the friction is generating that change. Or if you've sat on these chairs that are made of certain types of plastic, depending on the materials of your clothes, suddenly the whole chair is charged and you can actually feel the electrical charge. So for example, materials that gain electrons, so the rubber balloon can gain electrons, and hair loses electrons. You see the interaction there? So hair loses electrons easily, but the rubber balloon or the rubber can gain electrons easily. So what happens when I combine the hair material with the rubber material, once I make them interact, one is easily giving electrons and the other is easily receiving them, okay? And that's what generates the electrical charge. So electrical charge can also be seen as this unbalancing of electrons in a material or in any sort of body, okay? And this is just a reference of this. Remember, if anybody has any questions, and please just jump in. And so one thing that's also happening with electrical charges is that we mentioned the example of the balloon, right? And we had talked about the basic rule of opposites attract. And the corresponding rule that things of the same sign are going to repel each other. So in the end, if I go back here, if I grab a balloon and rub it in my hair, there's going to be an interaction where my hair is going to lose electrons. The rubber balloon is going to gain electrons. And when that interacts with another surface, a wall, for example, depending on the electrical charges, there are going to be forces that are going to be generated. And these forces are going to depend on different factors. So they're going to depend on the sign of each of the objects, of the charges of each of the objects. They're also going to depend on the amount of charge that is being generated, and those are the units we talked about. And it's also going to depend on the distance between them. Okay. And so let's look at this link here. I'm gonna copy. I'm going to jump over here and I'm going to copy this link. You have it in your PowerPoint, so but I'm going to copy it in the chat, and you guys can do this simulation at the same time I'm doing it. So go on to that web page. By the way, this website, this PHET, P-H-E-T, from Colorado, I think it's Colorado State University or something like that. Has very cool physics simulations to be able to kind of visualize things that we're talking about. And so just to kind of identify what we're talking about, this simulator, we can put charges in anywhere in this blank space, and we can see how the charges interact. And it's very cool because it's visual. So I'm going to do the following. An electrical charge generates what's called an electrical field. The electrical field is going to be a representation or a magnitude that has to do with the electrical energy. Give me a moment. It's going to have to do with the electrical energy surrounding the electrical charge. And the interaction between an electrical field and another charged object is what generates the force or forces. So we're gonna start using this simulator. You can do this at the same time I'm doing it. And I'm gonna ask you some questions. I'm gonna grab a positive electrical charge. Right now, we don't really have to think about the values, but this is a 1 nanocoulomb electrical charge. Nano means times 10 to the -9. That means it's a very small value. We don't need it to be very large for it to be powerful. We're going to talk about unit and magnitudes later on. I'm going to grab a positive electrical charge and put it here in the canvas. The arrows represent the electrical field. Okay. And the shading of the arrows represents the strength of the electrical field. Are we okay? So again, the arrows represent the electrical field that's being generated by this charge. The shading represents how strong the electrical field is. Okay. Look at the screen or your screens and interpret what you're seeing. What do you see there with regards to that positive electrical charge? What can you guys tell me of what you're seeing there? And the electrical fields. I need you guys to remember one thing. We're going to get to the formulas and the calculations when we need to get there, but I need you guys to analyze, look at something and extract information from it. What can you tell me from what you're seeing there? Andrea, please.
That it is.
I don't know, like if it's becoming like less strong, like when it moves, like it starts super strong and then less.
Well, you are correct, Andrea, but I'm gonna just tweak or correct something you said. Something very important right now is that the charges we're looking at aren't moving, are static. But I think what you were trying to say is that if I'm close to the electrical charge, it's very strong, right? But if I'm further away, it's weaker. Okay. That was by induction. Okay. That's a good observation. The closer I am to the electrical charge, the stronger the electrical field is. The further away I am, the weaker the electrical field is. Okay, good. Anything else you notice about the arrows, which is going to be hugely important with regards to electrical fields?
That they are pointing away from the electrical charge.
Yes. Thank you, Juan Ignacio. That's very important. It's actually going to be very important when we're talking about, because we're forces and interactions are going to have to do with signs. When we represent a positive electrical charge, the electrical field is going to be going outwards. That's how we represent. That's how we represent electrical. That's how we represent electrical fields. Okay, and I'm glad you guys are catching up on this because it's important. So something very simple that Juan Ignacio noticed that's very important is that the arrows are pointing outwards. Okay, that's actually very important. Okay, let's clear the field. Now I'm going to grab a negative electrical charge. I'm going to put it here. Now tell me what you see. What are you seeing that's the same and what are you seeing that's different?
It's the opposite.
It's the opposite. Yeah, let's dig a little bit deeper into that. Lisette, you had raised your hand.
I was going to say that they are inwards.
They're inwards, which is the opposite, which was Andrea said, but it's important. The arrows are pointing inwards. It's important. So for a positive electrical charge, the arrows are going to be going outwards. So the electrical field is going to be going outwards. Well, that's how we're going to interpret it. For a negative electrical charge, the electrical field is going to be represented like going inwards. Okay, the arrows are going inwards. Good job. What's the same from the other one? That's something that's different, but what's something that's the same? Anybody?
That it's moving.
No, I'm moving it right now just to see if you
They
guys are.
follow the chart.
Well, yeah, but I'm gonna stop moving it because I distracted you guys. Juan Ignacio, go ahead.
That it is stronger the closer it gets to the charge, either positive or negative.
Yeah, that's a good job, Juan Ignacio. That's important. The same happened with the positive and negative. The closer we are to the charge, the stronger the field is. The further we are, the weaker the field is. Okay, good. We good up to this point? Questions up to this point before we start mixing it up. Okay, now let's do the following. I'm going to put a positive charge here. And I'm going to put another positive charge. I'm going to put a negative charge. I'm going to put a negative charge here. What are you guys seeing there? What's happening? The two charges have, both of them have their own electrical fields. That's the energy that's being emanated. What do you see there in the diagram that I just put there when I put a positive and an electrical and a negative charge together? Anybody?
That one is giving and the other one is receiving.
If we look at, thank you, Anya. If we look at the arrows, the positive charge is emanating while the negative charge is receiving. That means that there is going to be a force. Okay, this is something important. I'm going to clear it. When I did this, there were no electrical forces there. Why? Because it's one charge with an electrical field, and that electrical field isn't interacting with anything. There's no forces here. The moment I put another charge, now there's two electrical fields interacting. The moment the two electrical fields start to interact, or a charge object interacts with an electrical field, then a force is generated. So, is it clear now about the opposites attracting? How are the interactions? One is going towards the other. So this is going towards here. There is an interaction between these two. And that interaction is going to be an attraction force. Now, what happens with that force? What happens? So what happens when I'm really close with the shading? How is the force between these two particles when I'm very close? Look at the colors there. How is the shading? How is the force?
It's very intense.
It's the colors are strong, so it's intense because we notice that it's very white here. So there's more interaction there. What happens when I move the charges farther away? What happens with the interactions? What happens with the interactions here in the middle with electrical fields? They start getting dimmer, you notice?
Yeah.
So the distance is going to be a factor in the force. And it follows the inverse square rule, where the force is going to be proportional to the inverse of the square. And that happens with a lot of phenomena that have to do with waves, because we could look at the electrical fields as waves, okay, as well. Okay. So I'm going to clear this. Now, what happens when I put a positive charge and I put another positive charge? What are you guys seeing there? What's happening with the electrical fields there?
They're like repelling each other.
Well, the arrows are going against each other. So the electrical field of each of the positive charges is emanating. So when they interact, there is also going to be a force between these two. But the electrical fields are repelling each other. They're going against each other. So this force is going to be a repulsion force. What's the same is if I'm farther away or close, it's still going to be proportional to the inverse of the distance, the strength of the force, but it's going to be opposing. And lastly, if I grab two negative charges, what's happening with the interactions of the arrows there? What's happening with the arrows there?
They are pointing each other.
They're pointing away from each other. So in the positive, they were going like this, which is a clash. In the other one, they're going away. So in both cases, we're going to have a repulsion force. So when the arrows are going in the same direction, that means that the electrical fields are attracting. When they're going either in the opposite direction or against each other, that's going to be a repulsion force. Okay. So with this simulator, we can kind of understand how these interactions occur, and electrical fields are going to be important for those interactions. Okay. Okay. Questions with questions here with the simulation? Any questions? No. Okay. We're going to be going back to these simulations in a bit. And so these interactions are going to generate that force. Now, that force is going to be defined by what's called Coulomb's law. And this is where we're going to start getting into the math. Like charges repel, unlike charges attract, or opposites attract, likes repel. And Coulomb's law defines the relationship that exists between two charged particles and these forces, or the force that interacts between them. And so Coulomb's law states that the force is going to be directly proportional to the charges, the value of the charges, and it's going to be inversely proportional to the square of the distance. And there's a constant here that relates this proportionality that's called K, that has to do with, actually, that's going to have to do with the material or the environment where the charged particles are located. Okay. And we're going to be discussing this and doing some problems in the next few sessions.